glance at it, it's got the same format. Okay, so I call the coefficient C instead of A. The point is that coefficient's constant everywhere in there. Do you think the set V has a zero element? Does it have a zero element? Yes. Yeah, it's just zero itself. For a given element of V, do you like the one that's already in there, the sum of the AXI's? Do you think there's an additive inverse? Yeah, it's just simply.
Oh, I had a question.
Sure.
So showing that ax to the I plus bx to the I is equal to c x to the I, where c is the same thing as a plus b, how does that prove that it's an element of V?
Good question. I think it proves that I really do have R as an element of V, because you take a peek at what's inside this big green circle. I think in terms of schematics, its format, it looks just like this. I think this is nothing more than a column expression of degree no more than n, for which each and every one of the coefficients is the same. When I say no more than n, I mean it is degree n or degree 0, because it's the only two choices. So I do think it claims membership by looking like that. Do you think scalar multiplication holds?
Yes.
Yeah, because when I bring the constant c in, I'm just going to get c times a for each and every one of its coefficients. Call k. All its coefficients are the same. So I do think that's a vector space. Oh, you guys! Shoot, my examples are too yeah. So can I raise a level of complexity?
Can I ask a question?
Yes, sir.
I'm sorry for asking so many questions.
I like it when you ask so many questions.
You're lying.
I am not lying. I'd be really honest.
Are we really going to come across scenarios where we find vector sets which do not just contain all the vectors in Rn space, and we have to talk about them and by properties about them?
Same question. Do you think that forms a vector space? Can I say it in English? Does the set of all solutions to the second order DE satisfy the axioms of vector space? Oh, by the way, I forgot to say about the scalars that are real numbers, with the usual operations.
Another way of doing that is the set of the family of curves which satisfy the differential equation.
The family of curves, those family of functions that satisfy the differential equation. Now, I have to confess, you guys, I have not talked about solving a DE. I just maintain you don't have to. Anybody?
I think it would, because the y would be or the collection of y's would be the family, and if you do something to that, say, particular instance, you would just get another member of the family.
See, I agree with you, but can you show it?
I don't know.
Let's prove it. I think he's right. You guys, can I do this? Can I just check closure properties? Just check closure properties. Okay, everybody, here's a question. If I let y1 and y2 be in my set V, and I allow y3 to be equal to y1 plus y2, the question really is this. Does y3 claim membership in the set V? Daniel, you're right. Now I'm just attacking you on, we're attacking all of us, on how you'd show it, how you write it out. Well, for me to determine if y3 claims membership, wouldn't I have to check to see if when I substitute y in 3 and for y everywhere, I get 0? So I think what I need to show is that when I replace y prime, y double prime on the left-hand side with y sub 3, I need to show you, the reader, that this is well, that. And if I can bridge that gap, I've shown you that y3 claims such membership. So let's give it a shot. I think I have the second derivative for this alternative name for y3. Minus 2 times the alternative name for y3. Plus 3 times that thing. So help me. If I differentiate the sum twice, do I get the sum of the derivatives? Or do I have some fancy product rule with addition of differentiation? Is a derivative the sum of two functions the sum of two derivatives? Of course it is. And so I think likewise, I got minus 2y1, I'm talking too fast. Minus 2 times the quantity, y1 prime plus y2 prime. Plus 3 times y1 plus 3 times y2. I can distribute. I can recollect all those terms. For example, I've got the first y1 double prime plus the third plus the fifth. And then I've got well, the second, the fourth term, the sixth term. But when you take a peek at these three terms right here, collectively speaking, they give you 0. I think it holds. I'll leave scale multiplication for you. I'm cheating. I'm in front of the class. I'm trying to beat that clock, you guys. I'm stealing the previous example, trying to keep a lot of it writing on the board. Sorry. All right, answer this question. Yes or no? Am I going to go about it the same way? Checking for closure for addition. Yeah, I think go about it the same way. As a matter of fact, with everything you see on this left-hand import, I don't think anything's going to change. The only thing that's going to change is over here, when I actually recollect these three terms together, well, 3 at a time, I should say. The first 3 terms gives me, second 3 terms gives me, and that's just e to the x, right? Oh, so it's not e to the x. This is actually 2e to the x, which is not the same thing as e to the x. So I guess I do not satisfy closure for addition with this differential equation. I will say in the near future it's a non-homogeneous differential equation because that's not 0. In my previous example, number 7, those were homogeneous DEs because it was 0 on the right-hand side of the equal sign. So, example number 7, I did have closure. Example number 8, I don't. Now, if I'm trying to determine in example number 8, if V really does form a vector space over that scale multiplication, excuse me, I said that wrong. In example number 8, if I'm trying to determine whether or not the set V is a vector space over the set F, what should I do in checking axiom number 2? What should I do in checking axiom number 2?
Take an arbitrary member and set.
So I think we should do nothing. Because since we've already proven that the first axiom does not get satisfied, then I don't need to worry about any other axioms. I know this is not a vector space. Did you guys see my point? Remember, I rephrased the question. Does it form a vector space?
So it seems like a lot of these we're able to determine just by looking at the first one. Would you say that usually the first one can tell us, like, are there going to be some that we work with where, like, all of them except for maybe number 8 won't work or something?
Yeah, give me 60 more seconds.
Okay.
That'll be my next example. Sorry, I just lost my train of thought. I apologize.
I'm sorry, is that an A10 or is that an A1 comma that you put up there? Or a comma in between A1 and A2? on the- Oh, okay. They
Oh,
look
right
like-
here.
Yeah,
Oh,
okay.
A1 and A2 are known.
Yes.
I'm gonna really mess this one up, okay? So you guys, I'm getting much more sophisticated with my operations. Actually, don't answer this question whether or not this is a vector space. Can I force you guys to jump around?
Well,
Yes.
I see a big problem.
With
You've
what?
got A2 times B2 in the bottom of the vector that's, or the matrix that's the addition of those two matrices. So wouldn't it be A2 plus B2?
No, I insist I will redefine addition. I will add two
You
matrices.
redefined it as multiplication, or what? how did-
Exactly. I redefined the addition. That's why I'm saying getting more sophisticated.
So have you just
Where?
broken math at this point?
No, I'm just saying addition now is defined in a completely different fashion in terms of multiplication. Here, and look at my scale of multiplication involves exponentiation.
What?
It's the way I define scale of multiplication. So humor me. Do you think if I add any two elements of this set B via this definition of addition, am I gonna get closure?
I think you've broken.
I think the word sure is just fine.
Yeah.
I think no matter what A1 and A2 are, or what B1 and B2 are, when I add A1 and B1, I get another real number. When I multiply A2 and B2, I get another real number. After all, closure, it does exist for multiplication of real numbers.
I think you broke my
Um,
brain.
Do you guys think I'll have closure for scalar multiplication? Ooh, you don't, Daniel.
Well, I was
No
just
eyesight.
thinking,
And if you
Yeah.
say no,
You're screwed.
you don't have to prove it in extended form. If you think an axiom is not satisfied, what you could do is just give me one example where the axiom fails. And if you could show me one example where the axiom fails, you've proven it does not hold for all cases. It's called the counterexample. Can you give me an example where this fails?
yeah, if a sub 2 is a negative number, and then k is 1/2, you would get a complex number for the.
Very nice. I agree, and I no longer have real entries. I think that's an example where I fail. Now, you can say that in words, the way you just did, or just say, well, if A is equal to this, and K is equal to this, then certainly K times A, which by the way is this, sorry, I meant this, is not an element of V. Because in V, these entries have to be real numbers. And you know what?
So,
Given that we found that second axiom doesn't hold, this is a test situation. I could say, I don't care if it holds or not. Check axiom 3, 5, and 7.
so when I'm looking at that, where in that notation does it actually say that they have to be real numbers?
Right here. In my definition, my set V, these entries have to be real numbers. That's an R if you can't read it.
Oh, okay, okay. Okay.
Do you guys think we could check axiom 5? What is a zero?
Yeah, it's
If there were a zero, what would it be?
Zero.
Zero.
All zeros, right?
0, 0.
yeah.
Why?
Because A times the 0 bar is going to be equal to did I call them A1s and A2s? I can't remember. Yes, I did. A1, 0, 0, A2 plus 0, 0, 0, 1, but this is the same as A1 plus 0, 0 plus 0, 0 plus 0, and A sub 2 plus 1. But this is nothing more than A sub 1, 0, 0, A sub 2 plus 1. Do you guys agree? Come on, you guys, wake up. No. something horribly wrong, where is it?
Oh, your addition on the
The
bottom.
top's okay, you meant.
Yeah, your
The
addition
H
is not defined.
Yeah, this is not the way I defined addition of these matrices. I actually defined addition of matrices by having in the last entries, the product of those two bases.
Yeah.
Which by the way is just which by the way is just
One.
A. Hold it,
Yeah,
I made
that's-
another mistake.
That's what's wrong.
My apologies. So that zero element plus A, again, Brad, I just answered the question.
I see.
Just be A right back
Yeah.
via that funky definition of addition.
Okay.
Did you see it?
Yes.
Makes the spring.
Well, yeah.
If negative A exists, what does it look like? Negative A1.
Negative 1, 0, 0.
1 over A2, you said it perfectly. So that when I add those two together, I get that 0 element right back, the one I listed on the board. So, question, is axiom 6 really satisfying?
I hope so.
Let's try it out.
All S is defined.
Oh, not,
There's a vector.
Yeah. So if we find that on the
Very nice. You guys look at this axiom carefully. It says, for every element in V, there exists a corresponding negative V satisfying this quality. And I think if my original matrix A had in its A2 position 0, then certainly that's not a real number. And so for all the elements in V for which this entry is the A sub 2 in the original one is equal to 0, there would be no corresponding inverse. So I think axiom 6 fails. Now, I like the way I asked my question. I said, if it does exist, show me what it looks like. That's a perfect question.
I get a little nervous whenever you use negative A, because it looks like A times the scalar negative 1.
I know. And that's why when I put the negative sign here, I'm talking about an element that has this particular quality, that when you add it to the original one, you get the 0 element right back, whatever the 0 element looks
So,
like.
so
Is there another way to write it, such that you just know it's the additive inverse?
Oh yeah, I think there'd be a much better way of writing it. I think the author should have done this.
Is that
Acetyl, excuse me. acetyl.
So, I'm just trying to look at this, and if I use your definition of addition and add A to A or negative A, I get the 0 vector.
True, but look at what the axiom asks very carefully in English.
Okay.
It says, for every element in the set V, does there exist a negative V bar? And I maintain, Brad, if A sub 2 is equal to 0,
Okay.
I got an element of V. But if A sub 2 is equal to 0, this additive inverse has this entry 1 divided by 0,
Which is undefined. Okay. Okay.
So I didn't write anything wrong above this. It's just that not every element A in the set V has a quality that's got an additive inverse.
So you'd have to define that it's all greater than 0 in order for that to work.
You could do something
Yeah,
like that, or
okay.
non-zero. That's what it really
Okay.
matters. You guys starting so slow. Can we check axiom 10? On the left-hand side, I've got R plus S times V bar, I'll call it A.
Can you maybe scroll that up a little bit?
I certainly can.
Squinting at the bottom there.
So I think when I take a peek at R plus S times A, I think that's just simply gonna be this. But that's gonna be nothing more than this. Parentheses, R plus S, times A1.
0. 0.
Stop. Skip the rest. Let's come down here to RA plus SA, which by the way is nothing more than R times this alternative version of A, plus this alternative version of A. Now, walking backwards, let's go ahead and multiply the Rn. And I think we're gonna get,
You missed your S.
thank you very much, I missed my S. Now multiply n.
A2 to the R2.
Base 2 to the odd power.
SA1.
1, 0, 0.
A sub 2 to the S.
Oh, excuse me, S, my apologies. That being the case, when I add these together, I didn't leave myself enough room. Is that an RA1 plus SA1, 0, 0, A sub 2R times A sub 2 to the S, excuse me. That same thing? Yeah, I think if I factor out an A sub 1, there's this. If I factor out, or not factor out, if I go downwards and use my basic laws of exponents, it works. Sorry guys, it's stalling. I'm trying to think of how to modify this. Okay, everybody, new notation. If I use this uppercase C, followed by some interval, I'm simply talking about all functions that are continuous over some interval on. I just chose the interval to be all reminders. If I asked you to consider C, actually, I don't know what to call this. I forget the notation. I think it's superscripts. That just simply means I'm looking at all functions whose up to the third derivatives, at least, are continuous. And so I would refer to Cn of I as being all those functions that over the interval I, up to at minimum, up to the nth derivative, all those functions are continuous. So let's not check to see if this is a vector space. It's way too big of a question. I'll ask a better question. Does closure under addition hold? Closure under addition. Okay, I gave you enough time to think. I'm sorry, that's lousy. I'm in class. I'm up against that clock. I can only give you so much time. It's not good. It's not the best way to approach this. But I gave you a few minutes. Let me dive in. I'm just going to run with it. Let's see what happens if I allow F and G to be understood to be my set B and let how about K be nothing more than F plus G? Question: is K really an element of set B? If it is, I've got closure. The first act is satisfied. If the answer is no, it's not necessarily V, then I know my set is not closed. So to check, I will simply, where am I at? See if K is, let's not. We already know the sum of two continuous functions is continuous. I think the condition I need to see as being that is going to be that one. So let's give it a shot. Let's take our function K, evaluate at 1, and see what we get. And if I get 0, then I guess I claim membership. If I don't get 0, I don't claim membership. I'm not closed. It's just that I define K to be F plus G, so somebody tell me what to write. And be careful.
F1.
Back to Math D, though. Math D. I can't hear you.
It's 0.
I can't hear you.
K of 1.
Poor pen. The blood's rushing down my arm.
That means that F plus G.
Guys, I'm getting dizzy.
Be 0?
You're wanting me to pass out. Isn't it just F plus G? You got it one? I'm serious about this. By definition, I define K. Now, I confess, back at Math D, the way you define the addition of two functions, a whole new function, is a function output is the sum of the outputs of the individual functions. But that's going to be,
0 plus 0.
well, wait a minute, how do you know G of 1, 0?
It was an arbitrary.
It was an arbitrarily chosen element in V. I was supposing that G was in V, therefore it already claims membership. So that's how we know. 0 plus 0 is equal to 0 if I'm not too sloppy, and therefore I do indeed think I have closure. Are you there? Do you guys think I could just finish with one last example? Just one. I don't know what number I'm on, 11. Wow, what a breaking, record-breaking day. I got through 11 examples. I'm sorry I'm so stuck, you guys, today on looking at the closure. It's one of the most important properties, though. I did do a few examples looking at the other axioms. I want you to do that as well. What do you think? Don't you think half the battle is looking at the inkboard and deciphering what the heck the set looks like? Yeah, I agree. And so I think I'm looking at all vectors in Rn, so that when I multiply on the left-hand side by the matrix A, I get B bar right back. Let's check for closure. Let's do what I suppose. That X bar and Y bar are actually my set V. And let W bar be equal to their sum. Let's check to see if W bar claims membership. Well, to see if it claims membership, I better multiply W bar on the left-hand side by check to see if W bar claims membership to set V. Let's multiply left-hand side of W bar by A and see if we get done. See if we get done.
B.
B. Well, B bar you meant.
Yeah.
Let's do it. I think AW bar is the same thing as A times X bar plus Y bar. Shoot, multiplication of matrices. We've already done this. We do have distribution for multiplication of matrices over matrix addition. I think I get this. Yes or no? Does X bar claim membership to V? Yes, it does. So what's another name for AX bar? B bar. Yes or no? Does Y bar claim membership for V? Yeah, I was assuming it does. Therefore, another name for AY bar is?
B bar.
B bar. So I think I get 2B bar and just simply B bar, right? No, wrong. I guess 2B bar is not the same thing as B bar. Therefore, I guess W bar in the end did not claim membership. Therefore, I do not get to set B as closed under addition. Are you there,
Yeah.
Chris?
I guess this is not really fair enough to this problem, but didn't we already agree that if there is a solution to, matrix A times X bar equals B bar, it'll be B?
Oh, there could be infinitely many solutions.
No.
However, even if that's true, when I take those two of those solutions, I add them together, it doesn't necessarily mean I get another solution.
Yeah, I was thinking of the rank. Let's keep those.
Oh, I see. I see your point. So, you guys, this is fundamentally important in mathematics, determining whether or not, with the definition of a certain kind of set, whether or not satisfy certain axioms. As a matter of fact, whole fields of mathematics behave in exactly the same fashion. For example, a geometry is a system of elements and rules that satisfy certain axioms. Matter of fact, talk about geometry is really interesting. Could be an algebra, could be a calculus. Let's talk about a geometry. When you guys look at high school geometry, or in geometry here at Sierra College, it's basically looking at what the Greeks accomplished. Now the Greeks tried to study numbers, but they got so upset. They said, things don't make any sense. Let's, as a whole society, let's give up. Let's not look at any algebra or arithmetic. It doesn't make sense to us. And they just stuck to geometry. That's what made sense to them. And along the way, historically speaking, as a society grew, they decided to prove all these theorems, and everybody had a different set of axioms or postulates. And a set of axioms or postulates is nothing more than a collection of statements you place faith in, that you believe in. It's just like a religion. It's like the set of axioms are your scriptures. I mean, it really is. And so one day, one mathematician among the Greeks was walking along and said, I'm sick of this. Every time I look at a different mathematician's proof, he assumes something different as a set of axioms. I don't like that. I'm going to not necessarily do new mathematics, I'm going to rewrite all these proofs in a book. He tried to write them in a book. His name is Euclid, and he failed. It ended up being 13 different books called The Elements. And he reformulated all the proofs up to that point by saying, here are basic axes, and he whittled down to, I think, oh shoot, I'm embarrassed. Is it 5? I was going to say 4. It's 4 or 5. Yeah, it is 5. And the 5th axiom is called the parallel postulate. Basically says this. Given a line, and a point not on it, there is a unique line passed through this point that's parallel to this one. It amounts to saying this: 2 parallel lines will never meet. And we all place faith in these 5 axioms for 2,000 years. And after about 2,000 years, we realized we were living in mathematical hell, because that 5th axiom does not have to be satisfied. And so there are some whole new sets satisfying a sub-collection of the set of axioms that Euclid had, namely the first 4, for which things still work. It's just that we sometimes refer to those as non-Euclidean geometries. But even an algebra or a calculus is nothing more than a system of mathematics based on a certain set of axioms. We're studying vector space this semester. You guys continue on your study in mathematics. You might study something called a group, which is a set of mathematical elements with an operation that satisfies a different set of axioms. Or a ring, or a field. Those are other things like vector spaces. They just have their own axioms. We're just concentrating on this particular collection of axioms. Chris?
Okay, so we got a vector space.
Tons. If I can determine of this weird set with these weird operations has dimension n, satisfies all the axioms, I can say, give it up. Let's just talk about Rn as equivalent. And what we do in Rn, we do over here in this vector space. Matter of fact, I will show you when we're done, that when it comes to 2 space, I'm talking about things like this. Or when it comes to P2, excuse me, I meant P1, set of all polynomials of this form right here. Or when it comes to the complex numbers, that's these things right here. Or when it comes to matrices of this form, with the usual set of operations. Who the heck cares what you're talking about? You put in special mathematical classes, they're all the same. They're all isomorphic. They're all the same as R2. The beauty behind showing that each of these collection elements behaves according to these axes means that I can now just say whatever power I have in here, I have power there as well. That's the beauty behind knowing that a particular set satisfies its axioms. That's utility as well, is showing that. Do I have my book? Oh, jeepers. Of course I do. So do you guys mind, can we skip Math 8? So could I not assign anything in 4-1?
What's the quiz going to be on tomorrow?
Chapters 2 and 3.
2 and 3?
It's nice you didn't yell at me for saying it.
Wonderful. Is there a Saturday lecture this?
There is Saturday.
All right.
Oh, I think you'll want to come Saturday.
Definitely be there Saturday.
Once I start chapter 4, yeah.
Yeah.
No 4.1?
No, I don't want to discuss, I don't want to sign anything out of Math 8. If that's okay.
Yeah, Math 8's not important.
Well, it's a foundation. So tomorrow quiz on just matrices and or calculus.
Okay.
It'll be very short.
Okay.
Oy!
Oh, did you bring our tests, or finish our tests for 32?
I really didn't.
Okay.
If you just forgive me, only because I had another class I didn't grade exams for yet.
Okay.
So I've been grading still.
Okay.
Oh, and you haven't passed out the quiz last week.
But again, I got bogged down with exams